Hello. In this tutorial, we are going to discuss recursion and go through some basic recursive functions and how to get repetition through recursion. Now, I should preface this by saying that all of what we're doing here could also be done using for loops or do or while loops in an iterative fashion, but oftentimes it's easier to express what you want to have happen in a recursive manner. Recursion has three properties that are important. The first is that the function will be defined by itself. So a function is going to call another function, but in this case, the function is calling itself. We also need to have a base case in that when we get to this case, we're going to stop calling, the function will stop calling itself. Otherwise, it would just go on forever. And the third condition is that there needs to be some work done to solve the problem or move us closer to that base case. Now, to begin with, I'm going to do something very, very simple. I'm just going to create a do something method, and I'm going to call it by passing this integer parameter, in this case 5, and I want to show the pattern of recursion and what's going to happen when this function calls itself again and again and again. So we'll create a public static void function called do something, and it's intentionally nonsensical in that it has no real purpose except to demonstrate the structure of a recursive function. When we get into this function, the first thing I want to do is to print out that we just started with n equal to n. And when we're done with the work, I'm going to say that we're ending with n equal to n. So the work that we're going to do is the pattern of recursion here. Let me fix the capitalization on do something there. Okay, great. So, like I said, the recursive function needs to call itself, so somewhere in here we're going to invoke do something. And it also needs a base case. In this case, I'm passing in an integer, and I'm going to subtract 1 every time I call this function recursively. So when n is equal to 0, I'm not going to do any work. I'm just going to say that I want to display to the user system out println. We're at the base case, so I'll stop calling recursively. Okay? Otherwise, I'm going to do my recursive call, and in this case, I'm going to do something on n minus 1. That's going to move us closer to making n equal to 0. So by subtracting 1 every time, if you pass me 5, n's going to be 5 here, n is not equal to 0, so I'll call do something on 4, and so on and so on. But before we do that, I'd like to indicate that we're here. I'm still working, and n is equal to n. So I'll call recursively again. Okay, like I said, recursion is a way of getting repetition. So you'll notice that in main, I'm just invoking this function once, do something, but it's going to actually run about 5 or 6 times, and we'll see a larger output here when we run this. So our pattern is, we've got a base case where we stop doing work. Notice there's no recursive call here. We have the function defined on itself, so inside of the function do something, I'm going to call do something again, and I'm moving closer to my base case, in this case subtracting 1 every time. My prints here, here, and here are just to indicate where I am in the running of my program. So if we compile and run this now, you'll see, let me grow this so we can see the whole thing. We start with do something on 5, so we just started with n equal to 5. It's not at the terminal case or the base case, so it's still working, and n equals 5. That's this line of code right here. So it's going to invoke do something on 4. Now at this point, the activation stack gets a new frame put on, and a new version of this do something function is called. And that's the output that we get right here. So n is 4 in this case, and all of the code is going to be completely run again. And this involves calling do something again, where n equals 3, where n equals 2, where n equals 1, where n finally equals 0, we get this base case, and we say I'm at the base case, so we'll stop calling recursively. And now notice that we're going to get all of our ending with 0, 1, 2, 3, 4, and 5 that comes out. So you can look at this output, and if you trace through methodically, you'll see that this is a way of getting repetition in our code. Even though we've only written this code once, it's going to call itself over and over and over again, and we're going to get that repetition. Now, looking at the output of this program, we should get a good idea of exactly what's going on. But to dive even deeper, our debugger within the NetBeans IDE gives us an opportunity to see even deeper what's going on by setting a breakpoint. And a breakpoint you can get into your program just by placing the cursor over the line number and clicking, and it will insert this red highlighted line and say, when the program gets to this point, I want to halt and examine what's really going on in the program. So it's actually quite useful to see what's going on in our program. Now, instead of clicking on or typing F6 to run, you need to come over here, and instead of running, you need to debug the main program. So click this one, and it's going to run, and you'll see this arrow here that shows we're right about to execute this line of code. If we go to our output, you see that nothing has been printed to the screen yet. So you can switch between the variable view and the output view, and this is really quite useful to us. Over here, we also have the call stack. So we were in main, and if we double click on this, it'll show us where we were. Right here, this gray highlighted line shows where main was paused, and it was paused when we invoked do something. Now, right above main, we've got main do something. If we click on that, it shows that we've gone into this function do something, and we're right about to execute this line of code. So if we look at our variables, you can see that n is equal to 5, and if I look here and put my mouse, if I click on it and move my mouse over the n, you can see n equals 5. So it's a good way to see what the variables actually have within them. Okay, I'm going to go back to my output, and over here we've got this step over, or you can press F8, and what it will do is it will not drill down into this line of code, but in fact it'll execute it. So if you click on F8 here, or you click on the step over, you notice my breakpoint is still there, but this green highlighted line has moved down. So now I'm just about to execute this code, and you can see the previous line of code, system out println, has actually gone to the output. So let's repeatedly press F8 and step into, notice n is not equal to 0, n is equal to 5, so it's going to drop down here to the else clause. It's just about to say I'm still working, so if we press this, we get the I'm still working with n equals 5, and it's just about to call do something again. Now pay attention to what's going to happen up here. Right now we've got main, which was running, and then it invoked do something, and now do something is currently active. There's only one version of do something. If I step over, it's going to drill down into, and you'll see we now have two versions of do something. We have the one that was running, where we left off right here, and we have this one where we're just about to say that we just started. Now look what happens when I put my mouse over this n. N is equal to 4 at this point. It's a different window on the activation stack. And if we look at our variables, n is equal to 4. Now watch what happens when I click on this frame. You'll see that n is still equal to 5 lower down on this activation frame. And this is key to understanding what's going on in recursion. Recursion calls the function over and over and over again, and it builds up this activation stack. So if we go back in here and we run, we step over, it's going to do a comparison where 4 is not equal to 0. We're going to drop down, and we're going to say I'm still working. Let's look at our output. We just started where n is equal to 4. If we drop in, notice we see I'm still working and n is equal to 4, so we're about to call recursively again. Now what do you think is going to happen up here? If I press F8, then we're going to get a new frame pushed onto the activation stack, and a new version of do something is going to be running. This time, in this frame, the n is equal to 3, since I'm subtracting 1 every time I go through. Back here, n is still equal to 4 in this frame. I'm going to run a little bit longer. Look at the output. We're about to get the I'm still working and n is equal to 3. If I push run again, here, this F8, it's going to push a new frame where n is equal to 2. Look at the variable here, n is equal to 2. And it's just about to say I'm just starting where n equal 2. We get that on the screen. It's about to say I'm still working and n is equal to 2. So it's going to push a new frame when it calls do something. So this is the power of recursion. The function is calling itself, and more and more and more are going on to the activation stack. N is equal to 1. It says I'm still working. There we are. Finally, we're going to call in this last version. We finally have our base case where n is equal to 0. If we go to our output and we step over, we say we just started where n is equal to 0. Now 0 does equal 0. So if we step here, we're about to say system out at the base case, and that's what we get. Now watch what happens. This was true, and then we dropped past the else, and now I'm going to say ending with n equal, and n is equal to 0 in this case. Okay, I'm going to do this. We get our ending with n equal to 0. Look at our activation stack. It's built up where n was 5, 4, 3, 2, 1, and 0. Now watch what happens here if I push proceed. One of them comes off the activation stack, and we return here where n is equal to 1. So we've come back. We're back down on the activation stack. We just finished calling this function recursively, and now we're going to say ending where n equal 1. And that's exactly what goes out to the screen right here. We're done here. So watch what happens to this activation stack. It goes down. It gets reduced by 1, and now n is equal to 2. If I run again, we'll get ending with n equal 2. If I press proceed, then we're going to lose another one of our frames off the activation stack. And if I run again, we'll get n equal 3 on the ending in the output. If I run again, more and more are popping off the activation stack. The function is finishing and doing its work. And this one's about to come off the activation stack. We come here. We just printed out where n equal 4, and I'm about to say ending where n equal 5. We drop down and done there. And watch what happens. We'll be done here, and we'll return to main. Now we're active only in main. We just finished do something, and if I hit proceed, then the program is done and we're finished. Okay, so take your time if you need to. Go back through and replay what I just did and see this activation stack is building up as the program recursively calls this do something again and again and again. Okay, I'm going to remove that breakpoint just so that we don't have to see it again. And let's look at another example of recursion here. Okay, similar to what we just saw, let's write a new function. I'm going to call this print n. And the purpose of this function is to take in a number n and print out that number from n down to 1. My base case is going to be when n is equal to 0, I'm just going to return and do nothing. Otherwise, if n is not equal to 0, then I'm going to system out println on n, and then I'm going to call print n recursively on n minus 1. So you can see the pattern we have again. I have my terminating case or my base case when I don't want to do any more work. I have some work that I want to do on the input, in this case n. I'm going to call the function recursively on itself. The function is named printn, and I'm invoking printn, and I move closer to my base case every time. Okay, I'm going to comment out my do something and just say printn on 10 and see what we get here. Let's run. And you see that we get the number 10, 9, 8, 7, all the way down to 1. Let's look in depth at what's going on here. I'm not going to do a complete activation stack trace like we just did on the do something, but if I pass in 10, where n is 10, it's going to print out 10, and then call printn on 9. That's going to put a new frame on the activation stack, where n is 9. It's going to print out 9, and then call printn on 8. That's going to push a new frame on the activation stack, where n is 8. And it's going to print out 8, and then call printn on 7. Okay? So real quickly, I'm going to put a breakpoint in here. I'm going to run with debugging. I'm going to very quickly show you how this activation stack is being built up, where watch the n is going from 10 all the way down. In this case it's 5, now it's 4, now it's 3, now it's 2, now it's 1, and look at how large this activation stack is. This is where n is 10, 9, 8, 7, watch these numbers going up, down I should say, 6, 5, 4, 3, 2, 1, and finally 0. I'm at the base case where 0 is equal to 0, so I'm just going to return, and my output has displayed 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 already. So if I proceed down, the activation stack is just going to be removed all the way down, one by one, until we're left with the output that we wanted here, 10 all the way down to 1. Now, watch what happens if I wanted to print out the numbers 1 to n rather than n down to 1. I can just swap these two lines of code like I just did. And now I'm going to do the recursion before I do the output, which means if you tell me to print n on 10, I'm going to have to do print n on 9 before I actually print out the value 10 to the screen. Let's look at how this would work. Let's stop the running here. And let's run this and see the output that we get. Now we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because I'm printing out, before I print 10, I have to print everything before 10. And if we insert a breakpoint very quickly, and we debug this, looking at our output, there's nothing there. Watch the activation frame. I'm going to show that it's calling print n over and over again. Nothing has been displayed here. You'll see the activation stack is building up, where now n is 2. The activation stack continually goes up until n is 0. Right, we get to our base case. And now we are going to look at our output. And I'm going to do this step out. And we're going to get our print here, finally printing with 1, and continue to do that. We'll get our 2. See how the activation stack is going down over here. We get 3 printed, 4 printed, 5 printed, 6 printed, 7 printed, 8 printed, 9 printed, and finally 10 printed. And then we return here into main. So if you want the output to occur after, just put the call to system.out.println after the recursion, and you'll get the work done in the opposite order. So the first version of printn had us printing from 10 down to 1. This version, with the recursion occurring first, is going to give us 1 printing up to 10. In addition to just displaying values out recursively, we can perform mathematical functions recursively as well. So let me take this breakpoint out. I'm going to comment out my print n, and I want to write a new function. This time this function is going to return an integer. It's not a void number. And I'm going to call it sum, where it takes in a number and it returns the sum from n down to 1. So our base case is, again, if n is equal to 0, I'm just going to return 0. Or you could also say if n is equal to 1, then I'm going to return 1, meaning the sum from 1 to 1 would just be 1. Okay, otherwise, if I haven't hit my base case, I still need to return a value, and that's key to this recursive function. Any mathematically recursive function needs to do a return case in the base case, as well as in the non-base case, I still need to do a return statement here, so don't leave that off. So in the case where I'm not done yet, I want to return n plus the sum of n minus 1. And what this will tell me is if I want to add the numbers 5 to 4, that's the same thing as saying 5 plus sum of 4, where sum of 4 is equal to 4 plus the sum of 3, and the sum of 3 is equal to the 3 plus the sum of 2, and so on down. Eventually we'll get down to where n is equal to 1, and I can just return 1. So we can invoke this by saying, back here in main, we're going to create an integer value, and I'm going to call sum on 6. And then I want to return to the screen that value. Okay, so if you know your math, the sum from 1 to 6, take a guess before we run, and here we go. We should get 21, right? How does that work? Well, it's 1 plus 2, plus 3, plus 4, plus 5, plus 6. And what we should get is this function sum is called with 6 to begin with, which means that 6 is not equal to 1. So we're going to get 6 plus sum of 5. Sum of 5 is 5 plus the sum of 4. Sum of 4 is 4 plus the sum of 3. Sum of 3 is 3 plus the sum of 2. Sum of 2 is 2 plus the sum of 1. And the sum of 1 is 1. So then all of that work is going to happen as the activation stack goes back down. And eventually we're going to return the total summation. In this case, it's 21. Now we could increase our summation. Here, let's say I wanted to calculate the sum of 10. I could run this, and I get the value of 55. And if you do the math, then sure enough, 10 plus 9 plus 8 plus 7 all the way down to 1 is equal to 55. Similar to the summation, I could calculate the factorial, or the product from 1 to n, by following that same pattern. I'm going to call this function factorial. It's going to take in an integer, and it's going to return an integer. And the base case here, let's just change the variable name so that you're not assuming it must always be n. So if a is equal to 0, then I want to return 1 in this case, because if I were to return 0, then the product between 1 and n, where, well, let's end it at 1 like we did before. We could say the factorial of 0 is equal to 1, in which case we could say where a equals 0, or we could say that the factorial, or the product of 1 to n down to 1 is equal to 1. Either one is going to work there, no problem. Otherwise, remember we must return a value either in the positive or negative case of the base case. I'm going to return a instead of plus. It's going to be a times factorial of a minus 1. So I'm still going down by 1 every time. Let's go back up here and comment out our sum call. Now let's call factorial on 6 and do a print of the value. Okay, so this is 6 times 5 times 4 times 3 times 2 times 1. Following this pattern, I'm going to move it up here so it's easier for us to see. Now coming up here, I want to call factorial on 6. So it's going to start off where a is 6, and that's going to return to us 6 times factorial of 5. Factorial of 5 is going to return to us 5 times the factorial of 4, and so on and so on and so on. If we run this, you'll get that the factorial of 6 is equal to 720, and if you perform all of that math, you'll see that our program is working correctly. The key to this program is noticing that no matter whether we're calculating factorial or sum or printn, recursive functions have a base case shown here and here and here. And if you're not at the base case, the function must recursively call itself. So you see that within the sum function we call sum, within the factorial function we call factorial, within the printn function we call printn, and that's the pattern that you'll see in all recursive functions. One more mathematical example is calculating the power. So let's say I want to know what 2 to the 5 is. This is going to be int result is equal to power of 2 to the 5. And then we'll print out result. Okay, now we haven't defined power yet, so let's do that. It's a static void int function power that takes in a base and an exponent. And if we wanted to work this out, you should know that anything to the 0 is equal to 1. So our base case is going to be that if the exponent is equal to 0, we're going to return 1. Otherwise, we're going to return base times power of base exponent minus 1. Okay, what this is going to do for us then is say 2 to the 5 is equal to 2, times 2 to the 4. And 2 to the 4 is equal to 2 times 2 to the 3, and 2 to the 3 is equal to 2 times 2 to the 2, and so on and so on. So we're going to repeatedly multiply base by itself again and again and again. And that's how we're going to be able to recursively calculate the power. I'm missing my public here, so let me fix that, and that will get rid of our error for us. And it's hard to return both void and int, so let me get rid of the void there. Okay, so now we've got this function power that takes in two integers, base and exponent, and for example 2 and 5, and it returns to me an integer. So if the exponent is 0, I'm going to return 1. That's my base case. Otherwise, notice recursively power calls itself here, and we subtract 1 from the exponent every time we call. So let's look at the output. 2 to the 5. Sorry, let me click run, and we get 32. Okay, let me close my debugger codes here. There we are. So 2 to the 5 is in fact 32. We can see 2 to the 10 should be 1024, which is correct. And you can adjust these, let's say 3 to the 4. That's 3 times 3 times 3 times 3. Should get 81 there. Very good. Okay, so that's looks like power is working nicely, but it doesn't work for negative exponents. So 2 to the negative 3, for example, is the same thing as 1/2 cubed. So let's improve this and show that we can have more complicated definitions. Since I'm able to return a decimal value, I'm going to need to improve this a bit to not work with integers, but return doubles. My base case here is still all right. Otherwise, I want to see if the exponent perhaps is less than 0. You gave me a negative exponent. Then I'm still going to need to return something here. And what I'll return is that I want to return 1 divided by, I'm going to typecast the base into a double. So 1 over the base, and I want to multiply that by power of base and exponent plus 1. So I'm doing a little bit of different work here. If you give me a negative exponent, I want to move closer to 0, so I'll need to add 1 to the exponent. And I'm doing a multiplication on 1 over the base. So if you say 2 to the negative 3, that's the same thing as 1/2 times 1/2 times 1/2. Okay, now, the key to this example is my base case is still where the exponent is equal to 0, but sometimes I'm calling power and increasing the exponent, and sometimes I'm calling power and decreasing the exponent, depending on whether the exponent is positive or negative. If it's positive, I still want to subtract 1 and get closer to 0. If it's negative, I want to add 1 so that I'm going to ultimately reach 0. And let's see what power of negative 3 looks like here. That should be 1/8, because it's 1/2 times 1/2 times 1/2, and sure enough we get 1/8 here written in decimal format. So those are numerous examples on how to work with recursion. The first example we had was this do something, and we took a lot of time to go through and point out exactly what was happening. The do something function does have a terminating case in n equals 0, and it calls itself, moving closer, trying to get to 0. We then did print n to display the numbers 1 to n, or n down to 1, depending on the order of these two statements. So flop those around and make sure you understand the impact of that. And then we moved into mathematically recursive functions, such as the sum and the factorial, by having our base case and also calling the function recursively. The key was there that we had to return a value no matter whether we were in the base case or not. And we just finished off now with this power function where we have a base case and we might move closer by adding, or we might move closer by subtracting off of the exponent. And recursion is a very powerful tool, and this tutorial should give you a bit of insight into the pattern of recursion. The key here are 3 elements. The function must call itself, There must be a base case where we stop calling, otherwise it will go on forever. And finally, we need to do some work and solve the problem getting closer to that base case. And that'll do it for this tutorial.